The engineers who designed the ship made a series of choices that no one asked for. They built a power plant that generates 78 megawatts, enough to run a small city inside a destroyer whose main weapon was a 155mm gun. They shaped the hull in a geometry that naval architects had abandoned after the Battle of Tsushima in 1905. They scattered the missile cells around the outer edges of the ship instead of clustering them in the center. And they replaced every mechanical drive shaft and reduction gear with electric motors so quiet the acoustic signature reportedly matches a Los Angeles-class submarine. Every one of these choices was called over-engineering. Every one of them was criticized as too complex, too expensive, too far ahead of its time. Every one of them turned out to be the reason this hull, the only surface combatant on the planet, can carry a weapon that flies above Mach 5. This is not a comeback story. This is a warning. Today, we are going to take apart 3 engineering decisions that cost billions and produced nothing for 20 years, and show you why they may have been the smartest money the Navy ever spent. Chapter 1. 32 ships became 3. Then the gun died. Then the railgun died. The Zumwalt class was supposed to be a fleet. The Navy originally planned 32 ships, then cut to 24, then to 7, then to 3. USS Zumwalt, DDG 1000. USS Michael Monsoor, DDG 1001. USS Lyndon B. Johnson, DDG 1002. As the fleet shrank, the cost per hull exploded. Construction cost alone exceeded $4 billion per ship. When you fold in research and development meant to be spread across 32 hulls, the number climbs past $7 billion. The ship's primary weapon, a 155mm advanced gun system, was supposed to fire precision rounds more than 60 nautical miles inland. But the specialized ammunition reached a unit cost above $800,000 per round. The Navy canceled procurement. 2 enormous gun mounts, the entire reason this ship was built, became steel furniture. Critics called it the most beautiful warship with no purpose. And by the numbers, they were right. 78 megawatts of generating capacity feeding a gun that drew almost none of it. The original weapon that was supposed to justify all that electrical power was the electromagnetic railgun, a weapon that would accelerate a projectile using nothing but current. That program was defunded in fiscal year 2022. The gun was dead. The railgun was dead. The critics appeared to be right. Then something changed. Chapter 2. The rescue that wasn't political, it was physics. In August 2023, the Zumwalt entered Ingalls shipbuilding in Mississippi. Workers cut out the gun mounts and began installing something else. By November 2025, 4 large-diameter launch tubes were seated in the forward hull. In January 2026, the ship completed build-to-sea trials, and the 78-megawatt power plant that had been called excessive for 20 years ran without a fault. A minor fire aboard the ship in April 2026 during integration work was contained by the crew without affecting the modernization schedule. Zumwalt was not rescued by a political decision. It was rescued by physics. Because 3 things the engineers built in excess turned out to be the 3 prerequisites for launching a hypersonic weapon from a surface combatant. Start with the first one, electricity. Chapter 3. 78 megawatts, 58 in reserve, the house wired for the future. Every warship needs power. But the way a ship generates and distributes that power defines what it can become. A conventional destroyer, an Arleigh Burke, runs 4 General Electric LM-2500 gas turbines, producing a combined 100,000 shaft horsepower. Those turbines spin through reduction gears, which turn drive shafts, which rotate propellers. The system is proven. It has been moving warships for decades. But there is a constraint buried inside that architecture. Almost every watt of energy goes into the propeller. The ship generates enormous power, but it is mechanically committed to propulsion. If you want electricity for a new radar, a laser, or a missile system that demands megawatts, you have to steal it from the drivetrain. There is no surplus, no margin. What you see is what you get. The Zumwalt engineers threw that entire architecture away. They installed two Rolls-Royce MT-30 gas turbines, 35.4 megawatts each, and two Rolls-Royce RR4500 turbine generators, 3.8 megawatts each. Total output, 78 megawatts. But instead of connecting those turbines to a gearbox, they connected them to a ship-wide electrical grid. The turbines generate electricity. The electricity flows into a common bus. And from that bus, power is routed wherever it is needed to two advanced induction motors that drive the propellers, to the combat systems, to the sensors, to anything the ship carries now or will carry in the future. Think of it this way. You build a house in 2005 with a 400 amp electrical panel when every other house on the street has 200 amps. Your neighbors laugh. The wiring is excessive. The capacity is wasted. 20 years later, electric vehicles and home servers arrive and demand exactly 400 amps. Your house is the only one on the block that does not need to tear open the walls and rewire. At cruising speed of 20 knots, the Zumwalt's propulsion motors consume roughly 20 megawatts. The remaining 58 megawatts sit in reserve, available for whatever the future demands. The 155mm gun consumed almost none of that electrical margin. The railgun, had it worked, would have consumed most of it. But the architecture was never built for one weapon. It was built for the margin itself. And there is a secondary effect. Those two advanced induction motors, 34.6 megawatts each, replace the mechanical gearboxes and drive shafts that every other surface combatant uses. No gears grinding, no shafts vibrating, no mechanical pathway for vibration to propagate through the hull into the water. The result is a 16,000-ton destroyer whose underwater acoustic signature has been reported as comparable to a nuclear attack submarine. A ship that large should be loud. This one whispers. 78 megawatts of power. But power means nothing if the platform carrying it gets detected and killed before it reaches firing position. The second choice the engineers made was even more controversial because it contradicted a century of shipbuilding. Chapter 4. The Shape Tsushima Banned. The shape radar cannot find. Every warship built since the era of the Dreadnought follows one rule. The hull flares outward above the waterline, wider at the top than at the bottom. The physics are intuitive. A flared hull pushes water outward when the ship rolls, generating a restoring force that fights the roll. It is why ships have not capsized for 100 years. Naval architects understand it. Sailors trust it. The Zumwalt reverses it. The hull slopes inward above the waterline, a geometry called tumblehome. The ship is narrower at the deck than at the waterline. It looks inverted. And the last time a major navy used tumblehome on a warship, those ships were sunk at the Battle of Tsushima in 1905. Russia's Borodino-class battleships featured tumblehome hulls. They capsized under fire. Naval architects spent the next century avoiding the shape entirely. So, when the Navy announced that its next destroyer would use tumblehome geometry on a 16,000-ton hull, the criticism was immediate. It will roll. It will capsize. It is a physics experiment, not a warship. It did not capsize. Captain Andrew Carlson, the ship's commanding officer, described navigating through sea state, 6 waves 13 to 20 feet high on a transit toward Alaska. He contacted his executive officer to report the conditions. The XO inside his cabin responded that it felt no worse than Sea State 3. The sensors confirmed it. The tumblehome hull, combined with a wave-piercing bow and a center of gravity planted low in the hull, delivered a ride so stable that the crew could not feel the storm. But stability was not the reason for the shape. Stealth was. A conventional destroyer 610 feet long, 80 feet wide, bristling with rotating radar dishes and antenna masts, reflects radar energy back to the source. That is what radar does. It sends a pulse, and the pulse bounces off flat surfaces and right angles. Every mast, every dish, every corner is a reflector. The Zumwalt has none of them. The superstructure is a single composite shell. The integrated deckhouse has apertures with every antenna and radar panel flush-mounted inside. No masts, no rotating dishes, no external reflectors. The inward-sloping hull deflects radar energy downward into the water instead of back to the sender. The result? A ship that displaces roughly 16,000 long tons but returns a radar cross-section reportedly comparable to a small fishing boat. And then the crew. A Burke-class destroyer displaces about 9,800 tons and requires a crew of more than 320. The Zumwalt displaces 16,000 tons and operates with fewer than 150 sailors enabled by the total ship computing environment, an integrated open architecture network that automates damage control, firefighting, machinery management, and sensor fusion across the entire hull. None of this, not the stealth, not the automation, not the silent hull, was necessary for the original mission. Firing artillery shells at a beach does not require a radar cross-section the size of a fishing boat. But closing to a launch position within range of a peer adversary's sensor network without triggering a response before the weapon is away requires every decibel of silence, every square inch of stealth, every megawatt of power. Invisible on radar, silent in the water, powered by a grid that could run a small city. For more than a decade, these capabilities had no mission. Then, the mission arrived. Chapter 5. Mach 5 Glide Body. Only one hull fits the physics. The weapon is called Conventional Prompt Strike CPS. A two-stage solid-fuel rocket booster lifts the payload to the upper atmosphere. At altitude, the booster falls away. What remains is the common hypersonic glide body, an unpowered vehicle that re-enters the atmosphere and rides its own shockwave at speeds exceeding Mach 5. A cruise missile hugs the surface and can be tracked. A ballistic warhead follows a predictable arc and can be intercepted. The glide body does something different. It skips across the upper atmosphere. It banks. It changes heading mid-flight. Every course correction rewrites the intercept equation for the defender, and by the time the math updates, the weapon has moved. No operational missile defense system on Earth has demonstrated the ability to solve that equation in time. The range exceeds 1,500 nautical miles. The glide body is shared with the Army's long-range hypersonic weapon, the system they call Dark Eagle. Same warhead, same physics, different launch platform. On the Zumwalt, the weapon sits in 4 large diameter tubes installed where the gun mounts used to be. Each tube holds 3 missiles, a total of 12 CPS rounds per ship. The tubes use cold gas ejection. Compressed gas pushes the missile clear of the hull before the rocket motor ignites. No flame touches the deck. No exhaust floods the launch bay. It is the same launch concept used in the Virginia-class Block 5 submarine payload module, and that is not a coincidence. Every round fired from the Zumwalt generates data that reduces risk for the submarine fleet. But the Zumwalt carries more than 12 hypersonic missiles. The rest of the armament sits in the Mark 57 peripheral vertical launch system, 80 cells arranged in 20 modules of 4, distributed along the outer edges of the hull. Each cell can hold a Tomahawk, an SM-6, a quad pack of ESSM for point defense, or a VLA for anti-submarine warfare. The cells are large, 28 inches wide, 283 inches long, rated to over 9,000 pounds per canister. Large enough for missiles that have not been designed yet. And here is the philosophy that separates Mark 57 from every other launch system in the fleet. On a Burke-class destroyer, All 96 VLS cells sit in two clusters amidships in the center of the hull. If a single cell suffers a catastrophic failure, the blast propagates inward toward the ship's vital spaces. The Mark 57 modules sit against the outer hull. If a cell detonates, the blast vents outboard into the sea. The ship loses one module. It does not lose the ship. The ship's current radar, the Spy-3, was designed for a different era. It can track targets along the coast. It cannot defend the airspace around the ship. The Navy is now evaluating a fix under the Zumwalt Enterprise Upgrade Solution, ZEUS. Installed the SPY-6V3, the same radar family used on the Flight 3 Burke, using arrays originally manufactured for the cancelled Constellation-class frigate. The hardware already exists. The ship has the power to run it. The question is whether 3 hulls justify the integration cost. If the answer is yes, the Zumwalt stops being a strike truck and becomes a multi-mission combatant that can defend itself and the ships around it. 3 ships, 12 hypersonic missiles each, 80 conventional cells each, a radar cross-section too small to target, and a power grid with room to grow. The margin finally had a name. Chapter 6. The margin finally had a name. In May 2026, the U.S. Navy's shipbuilding plan made it official. The 3 Zumwalt-class destroyers, USS Zumwalt, USS Michael Monsoor, USS Lyndon B. Johnson, were formally designated the fleet's first operational hypersonic strike warships. A program that spent 20 years facing cancellation had just become the most consequential surface combatant program in the world. The question worth asking is not how this happened. The question is why it could only happen to this hull. A hypersonic weapon that reaches 1,500 nautical miles needs megawatts of thermal management at the moment of launch. It needs to be pushed clear of the hull by cold gas before the rocket motor ignites a requirement that demands physical tube volume no standard VLS cell provides. And the platform carrying it cannot be detected on radar or in the water while closing to launch position. Stealth is not optional. Acoustic signature is not optional. Power is not optional. Volume is not optional. All 4 are mandatory, and they must all exist on the same hull at the same time. No surface combatant on Earth was built to satisfy all 4 except one. Built for reasons that had nothing to do with hypersonics. Finished in 2016. Criticized every year until the weapon arrived to prove why the excess was necessary. And that is the insight. The engineers did not design for the mission. They designed for margin. The IPS does not power a gun. It powers whatever comes next, CPS thermal management, a future directed energy weapon, the SPY-6 radar that draws megawatts no previous destroyer could spare. The tumblehome does not hide a shore bombardment ship. The electric motors do not silence a shore bombardment ship. Together, they hide a platform that must close to launch position undetected on radar and in the water because a hypersonic missile with 1,500 nautical mile range is useless if the ship carrying it is targeted before it fires. The Mark 57 does not carry today's missiles. It carries missiles that have not been invented yet in canisters rated for weights that exceed anything currently in the fleet's arsenal. And this is why the Pentagon now calls the Zumwalt a technology bridge. Every round fired, every megawatt logged, every approach run in stealth generates data that will directly shape the next capital ship, the Trump-class guided missile battleship, a nuclear-powered combatant displacing 35,000 tons or more with CPS tubes of its own. The Zumwalt is not the destination. It is the proof that designing for margin works. And the only reason that proof now exists is that a group of engineers spent 20 years being wrong in exactly the right way. Chapter 7. Was it a $7 billion mistake? Every engineering textbook will tell you, optimize for the mission. Build what you need. Cut the rest. The Zumwalt's engineers read those textbooks and then ignored them. They poured megawatts into a grid that had nothing to power. They shaped a hull to hide from radars that were not looking. They spread weapon cells to survive threats that had not arrived. For 20 years, that looked like arrogance. 3 ships instead of 32. A gun with no ammunition. A railgun that never fired. Billions buried in steel that critics said would never matter. But here is what the critics missed. The engineers were not building for the gun. They were not building for the railgun. They were building electrical room, physical room, stealth room for a weapon they could not name. They did not know what would come. They only knew something would. And something did. A weapon that flies above Mach 5, needs megawatts of thermal management, demands a launch platform invisible to radar, and fits only in tubes large enough to hold it. Every margin the engineers built, the margins that looked like waste turned out to be the price of admission. The question now is not about this ship. The question is, how many hulls in the fleet today are built so tight to the current mission that there is no room left when the next weapon arrives? And whether any navy on Earth has the nerve to leave room again, knowing that the room will look like waste until the day it does not. Chapter 8. The warning dressed in stealth coating. The Zumwalt is not a failure that got lucky. It is a warning dressed in stealth coating. Because right now, somewhere in a classified lab, a weapon is being designed that does not yet have a launch platform. It needs more power than any existing ship can spare. More volume than any VLS cell provides. More stealth than any hull can deliver. The engineers designing it already know what they need. They just do not know which country will build the ship that carries it. The United States already did. 20 years ago, by accident, while being laughed at. The question for every other navy on the planet is simple. Do you have a Zumwalt in your fleet? A hull so absurdly over-engineered that it made no sense at the time, but tomorrow it will be the only ship that can fire the weapon no one saw coming? If the answer is no, then the gap is not measured in dollars. It is measured in decades. Because you cannot rush margin. You cannot surge stealth. You cannot print megawatts on demand. You either built the room 20 years ago, or you do not have it when you need it. The Chinese Navy is watching. The Russian Navy is watching. Every admiral with a calculator is doing the same math. 3 ships, 12 hypersonic missiles each, a radar cross-section the size of a fishing boat, and a power grid that can run a small city. That is not a destroyer. That is a threat in triplicate. And the terrifying part? The engineers who built it are probably retired now. They spent their careers defending a ship everyone hated until the day the weapon arrived and proved they were right. So the next time you hear that a new military program is over-engineered, too expensive, too complex, too far ahead of its time, ask yourself one question. What weapon is being designed right now that only that ship will be able to fire? Because the Zumwalt was not a mistake. It was a down payment. And the bill just came due. 20 years from now, when the next weapon no one predicted arrives, which navy will have left room for it?